Hello everyone, welcome back to Tux Riders. This is another episode of the Finite Element modeling series. In this video, we wanna summarize what we've done so far, and I wanna introduce you some other exciting tools that we can use to perform the transient heat transfer simulation in the helical shape. Let's go for it. So, in the previous episodes, we used a set of different finite element solvers, open source finite element solvers, to solve this. Actually, first create this geometry, and then solve the equation, the heat transfer equation, transient heat transfer diffusion inside this shape. And so far, we used FreeFEM and FEniCS, two powerful finite element packages and languages. One is actually a domain-specific language, and that actually require you to derive the Vig form to perform the simulation. And then we also performed the simulation using the Elmer and Code Aster integrated into Salome, so Salome Mecha, as two examples of applications with user interfaces. And we also performed the simulation using OpenFOAM, which was actually a finite volume solver, mostly used for fluid dynamics, but we use it for performing this heat transfer problem. And the purpose was showing how we can import a geometry, a complex geometry that is not easy to create with out-of-the-box tools available in these programs. So we imported the mesh, we created the mesh externally, we imported the mesh, and we performed the analysis. But there are a lot of other tools, I can say, for performing these kind of computations using the Vig formulation we derived, also for structural analysis and solid mechanics, thermal analysis, and so on and so forth. And this video is actually intended to show you just a couple of them that I know. I haven't used these tools deeply in my work, and as a result, I don't want to make videos on them because, I'm not an expert on them, but actually I have checked them out. Most of them, actually, I have checked them out to run a couple of examples. And in this video, I would just want to show you so you can also try them, at least some of them that you find useful or interesting, and then see how easy it is, very similar to what we have done so far, to perform this kind of analysis in these software packages. So I start with one of the packages. This is actually one of my favorites. I use this package in my work, but because for our case, that was quite simple and straightforward and very similar to the FEniCS implementation, I didn't make a video on it. And that's called Firedrake. So Firedrake, I call it Firedrake code. So Firedrake project is actually code that is very similar to FEniCS. So in the end, it creates a very similar to FEniCS code in Python, but it has some nicer features that makes it easier to use with this in comparison to FEniCS, like for implementing and integrating like the imported boundary conditions from an external geometry. There are really nice features here, but the code in the end is very similar to FEniCS, as I said. So I want to show you just a couple of examples here. They have, I think they have a YouTube channel. I remember they had a YouTube channel here, and this is the GitHub project. So the project is still ongoing, and this is a live project. Although FEniCS has started to create a new interface, FEniCS, I talked about that in the FEniCS video, but this project is still is worth a check out. So let me show you a couple of examples quickly just to see how easy it is, and also to import geometries from external programs like Gmesh. So you see that the interface, the type of syntax you see here is very similar to FEniCS, and that's why I told you that I didn't want to make as a video on this, because that was very similar for our case. But generally, like for example, for writing the output in this case, and also control that you have on the solver parameters, this has some benefits to use this Firedrake, and it's also very easy to install, easier than FEniCS, I can say, because let me show you the documentation for installation. Yeah, this is for the installation. You can see that you download an install script, and then you run the install script using Python, and that's it. And then it starts to install the packages and compiling the packages like PETSI. And in this case, it's like I find it easier to interact with PETSI object, that is actually the Perl computing library behind the scene. So you see that here, for example, for importing a geometry externally, it's quite easy, because you can see that this kind of syntax that, for example, you have here. This means that doing this on the geometry, on the region that is labeled 4, and this is on doing this, this is diffusion term in a weak form on only the region that is marked as 3. And this is amazing, the way that this library, this package, provides the user with to deal with the external mesh. So generally, Firedrake is just as an easier, let's say, FEniCS. So you can check it out, and I think you will find it very, very useful. The other library that is in my mind to tell you is actually deal.ii, which is very similar to FEniCS and FreeFEM, and it is mainly intended to be used in C++. But the big advantage of this project, in my mind, in my opinion, is the fact that it provides the target user, the target you want to get started on this, with a lot of examples just out of the box. So the approach is the same. You need to define derive the weak form, and then if I can find the documentation, yes, oh no, these are the documentation and the tutorial. And then you can go on, start, you see that this is the graph of the tutorials, and you see that there are a bunch of tutorials here for different steps, for solving lots of different various types of partial differential equations. And at the same time, this is, for example, for massive parallel solution of Stokes flow. So it starts with the definition of the flow, and then the scheme to derive the weak form, and then it starts with to implement the code in C++. And this kind of code, for the other libraries that I want to show you, you will find these kind of notations being very common in other libraries, that they have directly access to the data structure, and you need to define your code in a way that dealing with those data structures. This is quite common in finite element computings, which is very similar to what I showed you actually in OpenLB, and also it's a little bit different from libraries like FEniCS and FreeFEM. They have a higher level language, I can say, but in this case it's lower level, but at the same time it has its own benefits, but it's not complex. If you know C++, you will find it quite easy to understand and quite easy to deal with. So deal.ii is one of the libraries that I wanted to tell you. The other package is actually called Kratos, which is written like this. So I should say, yeah, this is the name of someone, so I should say Kratos FEM. And yeah, this is the code. It's a multi-physics code. I think it's written in C++, and it has very nice parallel capabilities to be run in HPC environment. And there is a nice team behind it. I think they're in Germany. But let me show you some of the examples here. That it's also very similar to, and these are the galleries also, you can see. It's very similar to deal to, so you need to deal with your own stuff in finite element analysis. Let me open one of these things. I'm not sure if it points to the source code. No, but yeah, let's see how we can get started on this. Oh, download and documentation. So it says that we should go to the GitHub. So this is the code. And this is really, the nice aspect of Kratos is Perl features. I can say that it has a nice integration in OpenMP and MPI, so for both shared memory and distributed memory structures, and for fluid structure interaction. This is a type of simulation that is quite advanced. I pointed it out in one of the videos in this series. And it comes with also a couple of solvers, and instead of PETSI it uses trillions, which is very similar to PETSI. But yeah, so these are different features of Kratos. So this is just one of the libraries that I wanted to tell you, to show you, and this is quite nice to check out. Let's also check the capabilities. Yeah. So these are the things that I told you for thermal analysis, for safety, computational fluid dynamics, and for fluid structure interaction. So another similar library is called MoFEM or MoFEM, which is, this one is also, again, similar to deal.ii. It is intended to be used in C++, but the nice aspect about this is, yeah, it's efficient, but the bigger strong point of this library is advanced features for structural mechanics, because I think the people behind it, I know two of them. They are more on the structural mechanics and solid mechanics background, and as a result, this code has really amazing features for really like higher order finite elements or finite element schemes for more complex problems in solid mechanics. So these are, for example, some of the things that they have here. This is the tutorial that is available, for example, for heat diffusion, the problem that we solved in this series a couple of times. And there is also, for example, phase field stuff. As you can see, if you know finite element analysis, I told you we will describe it later in a dedicated series. But if you know it, you will find this kind of formulations in a more advanced versions of finite element. For example, for this one, when you want to combine a phase field model with some convection Navier-Stokes stuff, it will be quite challenging to implement. But wow, this is really amazing, and this is very difficult to be implemented in packages like FEniCS or FreeFEM. But in this case, you can see that it's very similar to deal.ii, and you define your code here, weak formulation, all these schemes for stability and for time stepping, and at the same time, it has nice interface to PETSI behind the scene. And this is for the you see that it says PETSI time stepping solvers TS. It uses that one to solve the heat transfer equation, which is actually very similar to the equation that we solved. And this is a typical amount of code, lines of code that you will see here in these kind of programs. But what I really like about MoFEM, I haven't worked with this in my daily life for all the works that I do, but with a couple of examples, I find it quite nice and easy to use, because as you can see, it has also, direct interface to the libraries behind the scene. In this case, for example, Boost or PETSI, and this is very nice for advanced use cases. I find this quite interesting, at least for me. And the other kind of tools that I want to introduce they're actually for multi-physics simulations and also physics engines simulations still related to finite element. One is SU2, that is again a C++ program for multi-physics design and simulation. This is also a nice code that you can take advantage of, and it's also very easy to get started with. Let me show you one quick start, but this is a little bit different from, this one is very similar to OpenFOAM, that you need to provide it with input file, and then it does the rest for you. So for example, in this case, it's kind of a aerodynamic dynamic simulation. It has its own meshing features as well, but you can see that it's more or less similar to OpenFOAM. The way that you define stuff is more like that. So it has also a theory guide and then a user guide. This one is one of the not as good as OpenFOAM. Still, OpenFOAM is the best in my opinion for fluid dynamics. But for multiphysics and fluid dynamics at the same time, this is a quite nice interface and program. And they have the YouTube channel to describe some of the things that you can do with this tool, and it's also quite up to date channel. And then there is another one, another tool that is well known, is called SOFA. So it's more like a physics simulation engine, but at the same time it has some finite element analysis behind the scene. And this one is I've seen in a couple of conferences they present, so they have a really nice team behind that they try to present in different conferences, relevant conferences, and present this. But there are lots of things for this SOFA. Let's go to the applications. I want to show you. This is more like something in between, like deal.ii. We really want to implement everything, and OpenFOAM that they have high level input files. This is something really in between. And these are, they have really nice biomedical application use cases and GPU computing. And then when you go inside all these subfolders, subcategories, you can see the different applications that they have provided. Multi-material tools. This is quite advanced. CGAL mesh generation. CGAL we have described. We have talked about CGAL before. And cardiovascular mechanics. So you see that these are really, really nice applications. Like here you see that implicit finite element simulation and fluid coupling on GPU. So when you go inside this, you can see that this is the way that the different demos and use cases they have with a link to the appropriate publications or source codes. And also for cardiac mechanics, you see that although it really looks like that this is something for just physics behind the stuff, like any other physics simulation software, but it is not. It is actually, it has some nice simulation finite element analysis stuff behind the scene. But similar to Code Aster and Elmer that we discussed, there is another tool very well known, especially in biomedical engineering field, called FEBio. And FEBio is a tool. This is actually equivalent to Abacus, but in the open source world, mainly developed for biomechanics. But still, it has nice like thermoanalysis, fluid structure interactions, fluid simulations as well, reaction, diffusion stuff, and as you can see, it's written here. But the users are really, so it's gaining more attention over years. And I haven't worked with this, I worked with this just a couple of times for some demonstrations, but I had colleagues working with this and they were really happy with this tool. This is quite nice, and it has nice integration. It has a nice post-processor and pre-processor and a graphical user interface similar to what Code Aster has, but it has also nicely integrated into other biomechanics related software packages for as the backbone for finite element analysis. But another well-known open source finite element code is CalculiX, and CalculiX is very similar to Abacus. And it is actually is developed with Abacus compatibility in mind. So the input file at Calculus is more or less compatible with Abacus. But there are also some convert tools that it can convert Abacus input files to CalculiX. But generally, more or less, it works very similar to Abacus. It has a user interface, but it's not very advanced. It's not very user friendly, but still it's handy to be used for some certain applications, but it's not as powerful as Code Aster, but still this is an option for solid mechanics stuff in the open source world. And it has also a nice team behind, and there are a lot of things you can find about this on the internet, because it's actually quite old code, as you can see here, being developed from 1998. And yeah, this is nowadays, at least in the 2 decades, 2.5 decades, it's a well-known code in the open source scientific computing community. And there are 2 other tools that I want to talk about. There are actually tools, not necessarily a complete solver stuff. One is MFront. So MFront is one of the tools that comes with actually CalculiX and Code Aster, but it's mainly developed. I mean, the usage of this tool, there is also a GitHub page, but the main goal, the main functionality of this code is actually to define material properties. So for complex material properties, something that you know, people in the Bacchus and ANSYS are usually proud of, and you may find it more difficult in CalculiX or Code Aster. This tool is intended to solve the problem, and even above that, it provides really advanced functionalities for defining material properties. So you can easily use this tool, which has actually, you can use it in C++ directly or use a high-level input language. And you can use this tool to define complex material properties or new material types and definition, contact, this kind of stuff, and then use it as, you know, material properties in Code Aster and CalculiX. So a combination of this with Code Aster, which I described in the Code Aster video, that is a very powerful solid mechanics and thermal analysis solver, it creates a very, very powerful environment for especially structural mechanics. And the other tool that I wanted to show you is actually a library that is widely used in scientific computing for coupling simulations, for creating multiphysics simulations, and it's called preCICE. And preCICE is not a solver tool, it's actually a coupling library that is intended to facilitate the coupling of different open source solvers. In this case, you can see that the OpenFOAM fluid mechanics solver is coupled with CalculiX structural mechanics solver to create a kind of FSI simulation. So you know, this is I've seen a lot of people who were very happy with preCICE, and it has a very live community like FreeFEM and FEniCS around it, that they have like the annual user days and a very in a very lovely environment, and lots of examples you can find on the community, on the tutorials, and also a YouTube channel, and a very active team actually behind the development of this tool. So make sure to check it out. This is quite useful when you want to combine different things. You know, for example, you don't need to actually using this. By using this, you don't need to limit yourself to multiphysics capabilities of different solvers. Like in Elmer is actually, or SU2, there are multiphysics simulation codes. But sometimes you find that, yeah, I know OpenFOAM and I want to perform fluid mechanics in that, and then solid mechanics in something more powerful, like in Code Aster, or you want to have your custom built finite element code for solid mechanics in FEniCS. This is the tool that you can use to couple those things together with minimum effort, I can say. So yeah, this is the tool. This is what I wanted to tell you about, and there are lots of use cases already built, and adapters, it's actually called, that you can use to couple different simulations. For example, you can see here OpenFOAM, CalculiX, and FEniCS are coupled together. And apart from these things, I wanted to tell you something that I've been told to check out, although, this is not something in, I'm not an expert in Julia language, but it's gaining more and more attention in scientific computing. And for related to a discussion, this is one of the libraries that is becoming more and more popular. As you can see, the number of stars, the number of commits. So this is a live project going on, a lot of users run it. This is a partial differential equation solver implemented in Julia and is available in Julia language, and is very similar to FEniCS or FreeFEM. So same concepts, anything is exactly what you saw, similar to what you saw in those videos and for those languages and libraries. But since it is in Julia, you can use, these fancy notations of mathematical stuff inside the language and these kind of things. But still, this is an ongoing project, but a lot of people have started to use it. And this is also a nice thing to check out, actually. And maybe in the future we will have, videos on this, because it's quite easy to use. And for also multiphysics applications, it can come quite handy. But so this is something that I think it's worth to check out. The interface it has for post-processing and pre-processing stuff, as you can see, and the way that it's very simple to implement stuff. You can see the code is very similar to FEniCS, actually. The way that a weak form is defined for the Poisson equation, steady state heat diffusion, for example, you can say, and with a few lines of code, you can have your problem defined, solved, and then written as VTK to be processed in PowerView. So this is what I wanted to tell you in this video. Sorry if I think it became a long video, but this is, I think, a nice wrap up on this series that we had to solve a single problem in different finite element programs. These are other tools that we could have gone for, but I think it's not really necessary because they're more or less the same, and my goal was to show you how similar it is to define the problem in these programs and languages, although they seem to be difficult to use, but they are not at all, and on the contrary side, they are very powerful. So I hope you enjoyed this video and this series, and hope to see you in next videos.